Alrighty, folks. So today we're going to be talking about section 3.2, which, as I mentioned last time, is about the derivative as a function. And it's not going to look a whole lot different, except instead of talking about f prime of a, where a is a constant, we're going to talk about f prime of x. One of the main differences is that our limit definition now only has one version, right? Because if we're replacing a with x, we don't want to have x show up anywhere else, right? If we recall our other version, when we were dealing with f prime of a, had x going to a, and had f of x minus f of a, and it had x minus a. And if we replace a with x, then we just get a whole bunch of nonsense stuff there, right? Because there is already an x to begin with, and it causes problems, right? So just for ease of notation, when we're using the limit definition to find the derivative of a function, then we're going to use this formula. Also introduced in this section is some new notation, right? F prime of x is the same thing as df dx, which is the same thing as dy dx. And this is also sometimes written as df dx like this, right? So that's just another notation. It means exactly the same thing. This is called Leibniz notation. But it's really just another way to write down the same thing. There's nothing particularly meaningful about it for us. It's just handy to have. So now we have a whole bunch of rules, right? So the rules from last section, things like the derivative of a constant equals 0, the derivative of just plain x equals 1. They give it its own rule this time. I don't really understand why, because it's actually just a version of the derivative of a linear function is the slope. So those are rules from last time. Those are preliminary rules that we talked about last section, sort of reformulated using Leibniz notation, right? We also have a couple of other specific function type to add to it. We have the rule that you will be using absolutely the most often, all the time, forever and ever, for power functions, right? And the rule for that is that we bring the power down, right? So this n comes down, then we multiply it by x to the next lowest power, right? So if it's x cubed, it becomes 3 times x squared. If it's x to the 21st, it becomes 21 times x to the 20. So you bring the power down to the front, make it a product, and then you change the power to be 1 less, right? And recall that power functions are specifically functions that have the variable in the base, and they have a constant exponent. On the other hand, if we have an exponential function, specifically what's often called the exponential function, the base e, then we actually have a different rule. The derivative of e to the x is just e to the x, right? We can actually do all of the other exponential functions, but the book decides to wait on it for now, because it's really handy if we have a couple other rules on our belt. Otherwise, we've got to sort of prevaricate for a little bit. But for now, the derivative of e to the x, which is not a power function, remember this is an exponential function. If the variable is in the exponent, it's an exponential function. If the variable is in the base, it's a power function, right? And those have very different sort of baseline rules for derivatives, right? And in addition to these sort of specific function types, we also have that the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. The exact same thing works for subtraction. And like our limit rules, it also works for constant multiples. So the derivative of c times f of x is going to be c times the derivative of f of x. Right? So we can pull constants out. We can break it up over sums and differences, and we've got a couple of baseline ones to work with. Right? So we might notice that these look a lot like the limit rules, and they're very closely related to it, given that the derivative is a limit. However, thanks to the way the limit that is this derivative works, we don't have a product or a quotient rule yet. That's what's coming next section. And they're going to be slightly different than the ones from the limit rules. And by slightly different, I technically mean very different. Those two rules don't really have direct correspondence, which is why they have their very own section. So let's get some practice using these rules. So find f prime of x for, let's see, 1, we're going to have f of x equal let's say e to the x plus 7. Right, and that looks a little weird because it's not actually one of the ones we have on our rules, right? So sometimes we have to be a little bit clever. And the cleverness that we're going to do is we're going to remember that for exponentials, sums in the power become products in the base. Now, if both of those had an x in it, we'd be stuck here, right? If both of those had an x in it, then I would have chosen a very awful example to get us started with, because we'd need the product rule for that. But this guy right here is a constant. Right? So f prime of x is going to be equal to the derivative of e to the 7 times e to the x. Right? And thanks to the constant, thanks to this rule, the constant multiple rule, that is e to the 7 times the derivative of e to the x. And thanks to this rule, I know that the derivative of e to the x is just e to the x. So it turns out that even with that extra plus 7 up there in the power, we still have, we still get the function back when we take the derivative. Right? That's not always going to work. You can do enough things to the power of e to the x that it doesn't stay exactly the same, but we won't be able to get to that until we have our chain rule. Right? So we're going to find f prime of x for f of x equals 11x to the 6 plus 6x to the 4th minus 3x cubed plus 21x squared plus 7. Right? So this looks like a big and complicated function, but all it is power functions added and subtracted from one another. So what we can do is we can look at each piece one at a time. Right? So if we look at this piece, right, we pull that 11 out because it's a constant, so we use this rule again. And then the rule for power functions says that we take this 6 and make it multiply. We have the x, and then the power goes down by 1. Right? For the next one, we pull that 6 out front. Only 4x cubed. Right? So I'm sort of doing it painstaking here. We can skip a little time, right? I know that these are going to be multiplied eventually anyway. So I could just go ahead, instead of making myself take an extra step there, multiply this power by the constant out front. So I go ahead and get a negative 9 x squared. I can multiply this power by the coefficient out front and get a 42x. And then this last one isn't actually a power function. It's this rule. It's the derivative of a constant, and that says we get 0. Right? So our final answer is 66x to the 5th plus 24x cubed minus 9x squared plus 42x. Right. Let's see. Let's do one more. Let's do f of x equals e to the x plus the square root of x minus the cube root of x squared. Right? So in this case, we can break it up by sums again. Right? I'm actually going to leave some room here because I want space to work. Right? This guy's pretty easy. His derivative is just e to the x, but this guy is maybe a little bit more confusing. Right? But considering we only have a very few number of hammers to work with here, right, that tells us that we need to remember something about our functions that will let this either be an exponential or a power function or a linear function or a constant. Right? And maybe that prompts us to remember that the square root of x is really just x to the 1/2. Right? And maybe that prompts us to remember that the cube root of x squared is just x to the 2/3. Right? So when we take the derivative of that, right? Well, we said we were going to take the power and multiply it out front. So we've got a 1/2 here. And then we take the power and we subtract 1 from it. So 1/2 minus 1 is negative 1/2. Right? Similarly here, we keep the subtraction straight down. This 2/3 goes out front. And then we have x to the 2/3 minus 1, which is 1/3. Negative 1/3, rather. Right? And if we want to simplify this, which we probably do, remember negative powers means it goes to the bottom of a fraction. So we can write this as 2 times the square root of x. And similarly, this negative power means we can bring it to the bottom of the fraction and have a cube root of x there. Right? So the power rule doesn't just work for integers, it works for any number. Right? So just to do another example real quick, if we have f of x equals the 7th root of x to the 4th, right? We just need to remember that that's x to the 4/7, and then we take the derivative by bringing that 4/7 out front. Take, I'll write it out this time because I have a little bit more room, which is 4/7 times x to the negative 3/7. And then when we simplify it, simplifying it generally should involve getting rid of negative powers by putting it on the other side of the fraction. So this becomes the 7th root of x cubed, right, down there on the denominator. Right? So those are our basic rules, and keep in mind that if a problem, and a problem will, have the instructions to use the limit definition of the derivative, you have to go back to last section and use this formula to figure out what the derivative is. Right? If it says just find the derivative, you're welcome to use any of these rules that we have here. Right? Just keep in mind to look for the instructions to use the limit definition of the derivative on some problems. Right? But while we have some rules, we're welcome to use those, and we should absolutely take advantage of that. Whenever we can. And next section, we're just going to get some more rules, so I'll see y'all then.